Morning, everyone. Can we all squish to the middle and all be friends because we have a giant room and we don't want to have to do huge amounts of running around like we made Eliza do earlier, please. Brian leads a small engineering team at Data61 called Confidential Computing. He and his team work on building privacy-preserving solutions, and Brian's going to give us the lowdown on linking data in a privacy-preserving way. So please enjoy.
Thank you. Now I'm terrified I'm going to clear my throat and you're going to all hear it very, very loud. But good morning, everybody. I'm Thorne on Twitter if you want to ask questions or heckle. The Confidential Computing team does a whole lot in the privacy-preserving space, primarily looking at can we do privacy-preserving variants of machine learning and also record linkage. Data61 works in a wider area than this, and there's quite a few people from Data61 here. I'm not going to go into any of the projects that they do, but I would encourage you to come up and say hello. We're a relatively friendly bunch. This morning, what I'm going to talk about is how record linkage works in general, and then how a privacy-preserving variant of that can work. So we'll get straight into it. There's quite a bit to cover. Record linkage as a principle, as a concept, is really simple. We want to link records, rows in one data set to rows in another data set. And this seemingly simple task is carried out all around the world in government, education, health, businesses, every single day. It's often done in spreadsheets and databases, by hand or by programs. And in general, the process looks something like this. We have two different data sets and we compute the similarity between those rows. That comparison table gets passed into a decision function, which has to determine, is this pair of rows an actual match or not? So this morning I'm going to use an example right through, and to warm up we'll just do a very simple record linkage operation using SQL. So the synthetic data set that I'm going to use comes from the Febrile tool out of ANU, and it's exposed through this Python library for record linkage called record linkage, which is very, very good. And we have two tables. They're both 5,000 rows, and there's an exact correspondence, and we're just trying to learn that correspondence. And the data set has the type of columns that you might expect. So you've got things that identify a person, personally identifiable information like name, address information, date of birth, things like that. Now, to keep the magic to a minimum, although the record linkage toolkit uses pandas data frames, which are excellent, and instead we're going to export to SQL and just keep everything on the table in plain sight. So to start with, if we have a shared key, in this case the social security number, we have in front of us a very easy job. We do a simple join, which in SQL looks something like this, and what we'd get out would be a table of record pairs. So in this case, we're mapping exactly where a shared key says so. But the much more interesting case is where we don't have a shared key, and then we have a bit more of a tricky task. It can be a bit daunting, certainly time-consuming, and more prone to error. Because what we'll have to do is use a whole bunch of weak identifiers, and we'll use the personally identifiable information and some rules to work out whether or not we believe a candidate pair is actually a match, and we'll separate those. So here in SQL, we can create binary features, which is just exact matching of particular features. Very straightforward. We're comparing surname with surname, and if one of them was null, we're trying to handle the missing value by assuming some value that's not 0 but not 1. And we're doing the same for all of the features that we have in this data set. Now, there's many ways to compare features that aren't just exact comparisons. If you can measure a distance between them, then you know, then you can use that distance metric to know how close the rows actually are to each other. And close can be a whole bunch of different definitions. It could be edit distance between words. It could be how similar words sound to each other. It could be temporal, how close rows are in time. It could be in space. Geocoded addresses, you can measure the physical distance between them. Things like that. In this case, we're going to stay very simple. And so we're going to just use these binary, almost binary, given when there's missing data, it's not going to be quite 1 or 0. And that will give us a table of mostly binary features for all of our candidate pairs. Now, looking at these samples, what we've got here is one row for every possible candidate link. And the features are showing, for the first couple of rows, that there's not good matches. The street number, address, postcode, state are all not exactly matching. So most likely those proposed links, those candidate pairs of records, are terrible. They're not a good match. Whereas the last ones, most of the features are matching. It looks like the postcode isn't matching on the last two, but all the other features are. So they're quite likely going to be a good record match. I know I forget my postcode and put down the last place I lived all the time. As a quick aside, how many candidate pairs do we possibly have here? This is a toy data set, right? 5,000 records on either side. That gives us 25 million possible links. And you might imagine that as we go into more real-world data sets, this problem just gets worse. So we'll make our job a little bit easier by using a concept of blocking or indexing. And that's a really important practical aspect of record linkage, which simply limits what we consider at all based on some other rules. Now here we'll take our candidate pairs from all records where the surname, the postcode, or the suburb have to match already. And this takes the number of candidate pairs down from 25 million to 130,000, considerably easier for us to work with. At PyCon AU a couple of years ago in Brisbane, Ridwan gave an excellent talk on record linkage where a lot more detail was spent going into QGram blocking, sorted neighborhoods, and how to deal with missing data, and a lot of the implications that you have in blocking, in record linkage in general. And I'd highly recommend checking that out. I'm gonna carry on. Before we got distracted by blocking, we had this big binary table of features, and we need to decide which ones are a real link or not. So we need to classify that. And that's simply, given these features, can we write a rule? Can we determine some rule that will say, I count these as matches and I don't count these, right? These are not matches. So we might intuitively just come up with something. We might say, well, if the social security number matches and the state matches and the name matches, then we'll consider that good enough. Or we could say, well, if 5 of the features match, that's good enough. Now, to get a bit of a feel for the data, I wanted to plot the distribution of how many features are matching. So this is after blocking. So we're not looking at all 25 million, but of those 130,000 left, I've counted the number of features that matched exactly, and it's dwarfed by when only 1 or 2 features match. As you might expect, a lot more people live in New South Wales that aren't actually the same person. So all of the data is kind of dwarfed by those first 2 columns. So let's enhance and look at the right, and we get a bit of a better picture. A lot of possible candidates seem to agree on 6, 7, 8, 9 features. And you might imagine that some features are more important than others. Some might be more reliable than others. And we could think about how to weigh those differently. And this could be from errors in the data. I mean, I'm certainly not going to point fingers at the emergency department's triage nurse who has far better things to do than triple check that she spelt the name right, or that they spelt the name right, sorry. And it could also be changes in the data. So features including but not limited to what we have here, address, phone numbers, names, date of birth, gender, all subject to change. As an aside, I'd highly recommend people to check out 2 blog posts, falsehoods programmers believe about names and falsehoods programmers believe about addresses. It's got some very interesting counterexamples to a lot of things. One more note on classification is if we had training data, say if we had known evidence of known good matches and bad matches, then we could perhaps train a machine learning classifier to do this. But we're going to keep it simple again. We're going to simply decide that a candidate will be a match if 5 or more features happen to exactly match. And that takes our, 130,000 candidates down to 4,800. Now we happen to know that there's an exact correspondence here, so we're looking for around 5,000 would be the perfect answer. And we're quite confident about those. Like we know that that seems to have separated most of the non-matches, but that's just kind of intuition. We'd really like to evaluate how accurate this actually is. So there are 2 metrics that are of interest here. One is precision, which asks how many of our proposed matches were wrong. So of those 4,800, were any of them a link between people that weren't the same entity? And in this case, no, we got that perfectly right. We had perfect precision. Recall asks, did we miss any? So were any of the valid matches not picked up by our simple rule of thumb that 5 of the columns had to match exactly? And sure enough, that simple rule didn't quite pick everything up, doesn't have good recall, or doesn't have perfect recall. Depending on the use case, this might be perfectly adequate recall. And we'd have to investigate what was missed, and was it particularly bad for some demographics rather than others? Now, I'd like to step back a little bit and think, okay, so all of this has happened, the analyst has done this work, probably they've done it a little bit more sophisticated than what I just walked through now, but they've done it all in one place, and they had access to the data locally. And that's the traditional method of record linkage. We trust, or have these semi-trusted linkage authorities or third-party businesses that do this as part of their business. Now here in New South Wales, that might mean there are the Centre for Health Record Linkage, there's SANT's DataLink, Curtin Centre for Data Linkage. A lot of these places, they all have the same requirement that you trust them with the personally identifiable information on which you're going to carry out linkage. So the rest of this presentation is going to consider not doing that, not having to trust anyone with this personally identifiable information. Now there are essentially 3 considerations, 3 things I'd like you to keep in mind while I go through the rest, which is what we're doing, what I'm proposing accurate? Is it actually private? And does it scale? So if we're going to be doing some sort of blind computation, we have to be confident about the fact that we're still doing well performance-wise in both accuracy and scale. Like if it doesn't work in real-world scale, it's not very helpful. And we have to deal with the real world, which we know has messy and missing and just generally rubbish data. So I guess to summarize that, we want to accurately do record linkage, knowing the data's full of rubbish. We want it to scale to population, so say millions of records, and we'd like it to do all that without sharing the information which is most useful for record linkage. So, hope you've had your coffee. Now, our team has open sourced 2 libraries that can help in this regard, and I'm going to go through the same example now, but using this instead. They're called ClickHash and AnonLink. They're available on GitHub. You can install them from pip. ClickHash will run on your normal computer, whether it's Windows, Mac, Linux, Python 2 or Python 3. AnonLink is the part that would be installed in a data center with assembler, and it's got compiled code to go fast. And that's a little bit more restrictive. I think it's Python 3.7 only. So now we're going to have a little bit more separation, and there are 3 players. And that means the data analyst can't just kind of look at the data and go, well, I'm going to use this column and this column, and I'm going to normalize them in this way. It means a lot of that has to happen in a bit more of a distributed environment. And so we imagine that there's a schema, or our tools take a schema that is the contract between the 2 parties that will instruct our tool ClickHash how to treat each column to encode the data. And I've just got a very simple example here of the schema, which is describing how we might encode a surname and how we might encode a street number. The details here don't matter too much, but essentially we're going to be encoding the personally identifiable information on the data provider, like at the data provider, at the source of the data, and then the encoding is going to be shared. Now, if you'll forgive my Jupyter templated shell command briefly, I wanted to show that we also had a command line tool, not just a Python library. And essentially, this would be the command that a data analyst is using to hash or encode their CSV file of personally identifiable information. They're passing in a schema that we just saw, and they're passing in a secret, horse staple, I think, and in this case, an output file name. Now, that would happen on 2 locations. 2 data providers would do this, and then they would upload it to a semi-trusted third party. So this is, I'll go into this in a bit. It's still sensitive information, but it's not your personally identifiable information, and it's a long way from that. So now, assume that we're sitting at the linkage authority. We've loaded those encoded PII, which I call clicks, into Python, and we can compute in the same way, the same process I introduced at the beginning, we can compute their similarity. So with a non-link, we can calculate the similarity, and that will simply go through. I'm passing in threshold here saying, don't discard anything. I want you to give me all of the results back. So that will go through and compute all 25 million similarity scores, like every row to every row in dataset A to B. And that's, of course, quite a lot, and that gets worse as we have larger datasets. 25 million comparisons of these cryptographic long-term keys, these encodings of PII, that can take some time. And usually you would use a default threshold. You might use blocking to improve the performance of this. So now that we've computed these similarity scores, which are all just a whole bunch of values between 0 and 1, how similar was this row to this row? We've got 25 million of them. We could have a look at those. I want to touch, though, on this is an expensive problem in the performance sense, but it is also very easily parallelizable. So we have wrapped a non-link inside a REST API, Dockerized it, containerized it, put it on Kubernetes, and scaled it to, I think we tried last week with about 128 cores, or 128 CPU cores, and we measure a throughput of around about 4 billion comparisons per second. And like what that translates to is essentially we can do a match of 1 million records on either side in under 5 minutes, which we're quite happy with. It seems to be approaching useful for real-world sized data problems. So now looking at these similarity scores, this is essentially the same graph that we saw before with the 8 or 9 binary features in SQL. We've now got a whole bunch of, no, that's not quite true. I won't say that. We're looking at the distribution of similarity scores between these rows, and the analyst can use this to make an educated guess about which scores are probably from these non-matches, like we had in SQL, and which scores are probably indicating a good match. And now, can you see the two distributions there? There's one very big obvious one, which is the normal distribution in the middle. And if we zoom in on the right, there's a very small distribution which hides all our actual matches. And so probably what we want to do is discard all of that huge normal distribution of non-matches and look in and work out, can we trust all of these similarity scores above 0.9 here, and are they good matches? So if we knew the answers, and in this case this is a synthetic data set, so we can peek under the hood and say, well, this is what the actual data is, and the matches here are shown in red. What I might slow down to describe this graph. On the bottom I have a few samples of records from dataset 1, and all of the scores, all of the links to dataset B that are above a similarity of 0.8, and they're colored by whether or not they're a non-match or an actual match. So very helpfully, the actual matches are all the highest scoring matches, and they're all looking like they're between 0.9 and 1. But you see out on the right there that a few actual matches are hidden down. And so if we just apply a really simple blanket rule and just say discard everything below 0.9, we're probably going to have low recall, as in some of the matches won't be identified, and that might be okay. So if we apply that threshold, and we'll just use that blanket rule of everything below 0.9 we'll discard, and we can just go through our similarity scores and cull those, we now will have a much smaller data set, and we can apply a classifier. Now we've found that a greedy approach works really well here. So a non-link implements a greedy classifier. You pass it this similarity matrix after we've done the thresholding, and it essentially picks those strongest links. Like it looks from the top for each entity and chooses the best one. And what we get out is a mapping. It's the decision model has output a mapping saying row 2751 in dataset A is the same record as 1016 in dataset B. I got those the wrong way around because I was reading the wrong column, but you get the idea. And in this case, we get about 4,700 links. And as before, if we have the ground truth information, we can evaluate that. So the same metrics can be applied. We find, again, we have really good precision. So we're finding good quality matches, but we've not got perfect recall. And depending on the use case, again, that could be considered good recall or maybe not. And that means that in a privacy-preserving way, a record linkage service has been used. The analyst's been able to link records without them being exposed to raw, personally identifiable information themselves. Now, I should definitely put in a side note here and say that when we're discussing probabilistic record linkage, there is limitations. There are limitations. You have to be aware that there's always the possibility of mismatches, and depending on the use case, this might not be a big deal, or it could be really unethical, deeply flawed, slightly idiotic. You might consider the effect of a bad link when you're aggregating queries across a linked data set for a report. A single link being wrong might not mean much. However, if you're doing something like predicting welfare debt and deciding when to send letters at Christmas using mismatched data, that might not be a good idea. So technology doesn't exist in a vacuum here. There are really important steps in terms of governance, legal, ethical implications that I'm not going to go into today. At Sherrill, they have a line that all studies using linked data must have an appropriate legal basis, and in most cases require ethical approval. And research institutes like us at CSIRO, any projects that use personally identifiable information have oversight from an independent body, an independent committee for human research ethics in particular. Okay, back on with the tech. So linkage today is essentially done in this way. The personally identifiable information is shared with someone who uses that to personally identify them. And we want to make sure, we want to get that same insight without having to share the PII. And we've seen that that's possible. And now I'm going to go into what we did, how that works. So we're still going to send something into a trusted, semi-trusted third party, but we're also going to do a little bit of computation at the data. Let's say we're doing edge computing on the edge. Maybe the first thing that comes to mind is, why don't we just hash it? And I mean, maybe that could work. We could hash each feature, or we could hash the personally identifiable information altogether. But we end up with exact comparisons. And so there are really two issues. Firstly, hashing doesn't necessarily protect much. If you know information about the underlying distribution of dates of birth in Australia or surnames in Australia, then you can attack that. And for better accuracy, we really want to do a probabilistic linkage. So we deal with the types of errors in the data we know are present, like misspellings. So we need a way to encode the PII. Now, perhaps XKCD has some advice while I take some water. Okay, I'm hearing a few murmurs, and we've got 5 minutes left. So we've established really that hashing is not going to work. And perhaps the other tool in the security toolbox would be, we could encrypt the data. Maybe, but comparing encrypted data, well, there's really two ways you do that. Either you're decrypting it, which just brings us back to step one, or we're using some new methodology like secure multi-party compute or homomorphic encryption. And that looks really promising, and I believe that will be the eventual place that privacy-preserving record linkage goes. But it's not necessarily practical for real-world scale today. And as an aside, cryptography is not all set on this, and cryptography tries really hard not to be in the move fast and break things way of doing things. So we're going to look at 3 concepts for the last couple of minutes, which is what we used in the ClickHash and on-link demo I just gave. They are Bloom filters, changing Bloom filters into cryptographic long-term keys, and then comparing those. So the Bloom filter is really cool. It's a very simple data structure, and it really has two things you can do. You can add keys into it, and you can query, was a key part of it? So here, we're adding the key banana into a Bloom filter, and we simply hash the string banana a couple of times, and when you hash that, you get, when you hash banana, you might get a number out, which we're going to treat as an address in the Bloom filter. And all we're going to do is look at that address and set those bits to 1. Easy. You might do that for multiple keys into one Bloom filter, and then when you want to ask, is something in a Bloom filter, you just do that again, and you see what the results were at that address. So if we hash grape 3 times, we get 3 different addresses, and it's a probabilistic data structure as well. So if we got all 1s back at the addresses, then it tells us that the filter probably contains the key, Not necessarily. There are false positives. And if any zeros were found, we know for sure that that exact key wasn't hashed into that Bloom filter. So you're probably very aware that a hash function works in a way that if you change the input slightly, the output changes drastically. And that's not really what we want if we're trying to get probabilistic data linkage. And so if we just hashed a name using a cryptographic hash function, that's not going to be useful. Brian spelt with a Y and with an I is going to hash to completely different values, for example. So instead, we're going to use n-grams, which are really quite simple tokens of a string. Here I've got unigrams and bigrams of the word Smith. And combining n-grams into a Bloom filter really gives us the cryptographic long-term key. The only other piece to the puzzle is an HMAC, which is a keyed hash function, essentially, and that gives us a bit more of the security. I'm going to show the overall view of the system now, just to kind of walk through and put us into perspective. So on the data provider side, we had the personally identifiable information, and that would be encoded. Now the HMAC comes in here because that's where the shared secret is useful. 2 data providers require that, plus a schema, and they encode their information, upload that to the top box, some linkage authority. A non-link can take that and compute the similarity between all of the cryptographic long-term keys, or this encoding, and then pass it to a decision model. And we saw an example of the greedy solver. Now, doing the actual comparison is really easy. The Bloom filter really gives us this. If we can count the number of bits which are in common, then we can compare them, and we can come up with some number between 0 and 1. Now, I won't go into the math of how that works, but all it requires is an ability to do a pop count and an AND operator between the clicks. So we can do that really fast. And I've been through the decision model. It's really simple. We just take the strongest links for any entity in a greedy fashion, and that really gives us an error-tolerant, privacy-preserving record linkage thing. And so we can accurately carry out record linkage, knowing that the data's full of rubbish, scale it to millions of records, and do it without sharing any of that personally identifiable information. That's my talk. Thanks.
Thank you. And
Oh,
thank you for putting up.
I get a cup.
Yes,
Thank you.
a mug. Go fill
get
it
a
with
mug?
coffee, tea,
I
whatever
will.
now.
I will. Thank you.
Maybe wash it first. We've got